Welcome to Picture Language Seminar. It's a real pleasure today to have Semyon Dyatlov from Massachusetts Institute of Technology. He's going to tell us about resonances for open quantum maps. It's related to Fractal Uncertainty Principle, and we're very much looking forward to hearing your talk. So Semyon, why don't you share your screen?
Hi, everybody. Thank you for inviting me to speak again in the seminar. I think last time I gave a talk was late 2018. So it was 3 years ago. And today I'm going to talk about similar things, but in a different setting. So this is the context of this work. It's in a field called quantum chaos, and one of the questions, one of the objects that quantum chaos studies is open quantum systems where the underlying dynamics is chaotic. So there are various settings in which you can study this. Some of these are experimentally actually verifiable, such as scattering by obstacles, but today I'll focus on a toy model known as open quantum maps. So for all of these open quantum systems, a much studied issue is whether or not you have what's called a spectral gap. So you can think of open quantum system as some kind of wave or Schrodinger equation in a, let's say, non-compact manifold where energy can escape to infinity. And so most of the energy is expected to escape to infinity. And then the question is how much of the energy remains in, I guess, what physicists would call the interaction region. So it would not scatter away to infinity. So spectral gap is roughly equivalent to saying that local energy decays exponentially fast. So that's fast decay of energy. It means it's hard for waves to become trapped in the interaction region. They do have a strong tendency of getting out. And so this has been studied again in various contexts since, I want to say the 70s. I'll mention the literature a bit later. And it was known that a spectral gap holds under something called a pressure condition, which basically means that the set of trapped trajectories of the system has sufficiently small dimension. That's the easiest way to think about this condition. And so it's still an open...
Is this a fractal dimension or integer?
There is something called topological pressure, which is the more correct quantity to study. In the most basic cases, the Hausdorff and Minkowski, all the dimensions would coincide of the trapped set, and then you need this dimension to be small. But in general, when Lyapunov exponents are variable, there is this pressure quantity, which is the correct quantity to study, but I'm not going to define it in general. So, it's a basic example. If you do scattering by several convex obstacles, if you move the obstacles sufficiently far away from each other, this condition holds. If you put them too close, then it will fail. And there are various, computations for this pressure and asymptotic. I remember one of the old things for convex to compact was actually done in Harvard by McMullen, of how this pressure behaves. But I digress. So for some open chaotic systems, it was known that you have this exponential decay. And in general, it's still an open question whether you have it or not. But there is some recent work which gives an indication that maybe it should be true for all systems, namely together with Zal and with Bourgain, in combination of these two papers, proves the existence of spectral gap for all systems of a specific kind, which are convex co-compact hyperbolic surfaces. I'm not going to talk about hyperbolic surfaces, but that's why I wore this T-shirt. You can see it's a plot of this T-shirt is from a conference, and it's a plot of resonances. It doesn't look like a plot of discrete points. There is a lot of interesting structure there, but it's a plot of resonances for hyperbolic for a specific hyperbolic surface, courtesy of David Borthwick and Tobias Leicht. And so if that's something that you put on a T-shirt, it means it's worth studying, right? So. So we did that, and I think that was an important result, but I'm not going to talk about this result today because the technology is complicated. And instead, what I will do is I'll present an elementary, a setting where you can have a more elementary approach, or rather, it's the same approach, but its execution is much more elementary, and we might be able to actually understand, maybe appreciate it better this way. And so this will be this open quantum maps, and this will be a specific kind of open quantum maps that I'll introduce in a moment. And so this is just general motivation for why we study this. So what are open quantum maps? Well, so when the key object associated to open quantum chaotic systems that I'll study is called resonances. So this is this numbers that were pictured there. You can see kind of, if you go down, you can start seeing that it's a discrete set. So resonances are, I mean, I write this kind of vague definitions of complex characteristic frequencies of decaying waves. So, you know, the energy is allowed to escape. Now, if you have a closed system, such as, say, the wave or Schrodinger equation on where the space is given by a compact Riemannian manifold, for example, then you know, that's something we study or we teach in basic differential equations courses, that you can expand the solution in terms of the eigenvalues of the Laplacian. Now here, when you open up the system, the Laplacian generally doesn't have discrete L2 spectrum, but you can define some other version of discrete spectrum for it, called the set of resonances, and they have they are complex numbers. They have real and imaginary parts. And the real part tells you the frequency of oscillation, and the imaginary part gives you the rate at which the exponential decay happens. And so you could expand solutions in these resonances. So I'll give you an example. Well, that you might not be able to hear that. Let's see. I might have to. Hello? Oh, okay, it got disconnected. One moment. Okay, hello? Should be able to hear me now, no?
Yes, yes.
There we go, yeah, because so while I have an object, right, and I'm hitting it, and what you hear is, this is not an object designed for that purpose. I don't have any musical instruments that I can use here. But you see, when you hit it, you hear a pitch, and that would be the real part of the leading resonance. But then you also know that it dies out exponentially. It doesn't stay forever, right? And so the speed of exponential decay, so basically the reciprocal of how long you hear the sound would be the imaginary part of the resonance. Anyway, so that was my demonstration here. Resonances are something that people study, and they have a manifestation in our physical world. Mathematically, they are more of a pain to define, but this can be done. And so when you study these resonances in chaotic systems, you study things such as spectral gaps, and you also study counting of resonances. So fractal Weyl laws, which, you know, the counting situation gets much more complicated and less known than in Weyl laws for, say, compact Riemannian manifolds. And there are various applications here. I just for kind of to just flash that there is one picture of somebody applying resonances to Google matrix. Not that I can comment on any details of that paper, but it's anyway, it's a kind of object whose distribution, here's something about Weyl laws, has been actually extensively studied and appears in quite a few places. Okay, let me full screen again. All right. So yeah, so open quantum maps, they are a popular model in open quantum chaos, and that's the model that I'll study. So it's usually considered toy models, even though there are some proposed experiments. And another thing that is very nice for open quantum maps is because they're families of matrices, you can actually do numerical experimentation with these much simpler. So, for example, the plot that's on my T-shirt, that takes quite a bit of effort to actually compute these resonances for convex co-compact hyperbolic surfaces. For open quantum maps, I can do it myself using just MATLAB and, you know, finding eigenvalues of a matrix. So, all right. So now, finally, the overview is done, or the kind of motivation is done, and I'm moving to the actual setting that I'll study today. So I'll first talk about open maps that I'll use, the classical side, and then I'll explain in somewhat vague terms how they're quantized. So the maps I'll study today will be open Baker's maps. They're very neat maps because the fractal set of trajectories becomes a kind of an arithmetic Cantor set, which makes it easier to study. So what are open Baker's maps? Well, let me give you a basic example, which is a Baker's map that corresponds to the mid-third Cantor set. So these are maps of the square, just 0, 1 squared in x and psi. So that's the square that you see here. And this map is, the map corresponding to the mid-third Cantor set is pictured on the right. So imagine you have your square, and then you split it into 3 parts, 3 vertical strips of equal width. Then you throw out the middle part. That's why it's white like that. And then the other 2 parts, you dilate them. So you stretch them horizontally by a factor of 3. You expand them, and then you contract them by a factor of 3 vertically. And then you get, and then you place them into these 2 horizontal strips. And nothing goes into the middle. So this map is a relation. It's not everywhere defined because this middle part you throw out. And you can see that's why I drew these letters A and B, that you can see that it's not rotated, it's stretched like this. So this picture on the top is mapped by this map to the picture on the bottom. Sometimes I say this turns a French flag into, I forgot, what is that, Slovenian flag? One of those tricolor flags. It's not the Russian flag. The order is not right. But it turns a French flag into this other flag, like that. But it does it by stretching as opposed to rotation. Well, you can define this thing in general. So how do you define more general maps like that? You fix a number called the base. It should be at least 3 to make things interesting. Then you fix some subset of digits modulo this number. It's called the alphabet. And I'll always assume that the alphabet has at least 2 digits and is not the entire set here. Because otherwise you get kind of a trivial case. And so we assume this, and then here is the formal definition of the canonical relation. Okay. But it's really a generalization of what's pictured on the right. And so this is a basic model of an open chaotic map. Chaotic is because it has hyperbolic behavior. You have exponential stretching and contraction. And this is what leads to chaotic behavior or unstable behavior under perturbations of the initial trajectory. Open because you have this middle that you threw out. So it's not everywhere defined. So if you think about, say, some function living on the square, you kind of, if you had some energy here, you throw out the middle. So you think of this throwing out as something traveled off to infinity or was absorbed by some kind of absorber or whatever other, physical model you're thinking about. All right, so that's our classical side. And the fractal sets come into the domain and range of powers of this map. So if I look at this map, you can see that, I don't know if this picture does it justice. It's a correct picture, but might be a bit confusing. But for instance, if I iterated my map twice, maybe I'll go back a slide for a moment. If I take this map and I iterate it twice, what will happen is that these 2 middle pieces, where the letters A and B are in the bottom, they will also be thrown out. So you end up with 4 pieces, and then they'll be stretched into 4 strips rather than 2 strips. And they would be corresponding to numbers 0, 2, 6, and 8 mod 9, which is an approximation of the mid-third Cantor set. And so when you do it, when you do it several times, what you get is the following picture. If you look at the domain and the range of the power of this map, so you tend to throw out a lot of things, you get this picture that the range of the map is going to consist of a bunch of these horizontal strips. And the domain, so the place where it's defined, will consist of a bunch of vertical strips. And so the way the map acts is, here this all of these things are color coded, so you can trace the path of each rectangle if you wanted to. But you can see that, for instance, here what happens is I take this chunk on the left, these 4 strips on the left, and then I dilate it, and then it becomes this 4 strips at the bottom. And then 4 strips at the right become 4 strips at the top. And then I apply the map again. So I take this kind of 2 by 2 thing on the left, and I dilate it, and I get this thing that's at the bottom, and so on. So you get this thing. And the places where this domain and range are encoded by the discrete Cantor set. That's the object that we will study a lot in this talk, which is just numbers written base n with k digits, where k is the number of times I iterated, where digits are in the alphabet A. So if A is 0, 2, and m is equal to 3, you just get the usual, approximation of mid-third Cantor set, or a discrete version of that. All right, so that's where fractal sets come into the picture. Now, well, maybe you're more used to the Cantor set as a subset of 0, 1. So how do you obtain that one? Well, you can think about the limiting set here. So you take, well, you just look at this picture here, and you think, what happens as I let k go to infinity? So which psi coordinates, so which vertical coordinates will still persist? And you get the mid-third Cantor set. And in general, you can start with any base in alphabet, and you get this corresponding Cantor set, which is numbers between 0, 1. When written base m, they only have digits in the alphabet A. And this set has a well-defined dimension, Hausdorff, Minkowski, in any kind of dimension you want. Well, not for you, but any kind of reasonable dimension would be this number delta, which is log of the number of elements in the alphabet over log m. And because of my assumptions, it's strictly between 0 and 1. Yeah, so so for example, the mid-third Cantor set, the dimension will be log 2 over log 3. Okay, and then in this setting, this quantity called topological pressure is just the dimension minus s, and it's a function of s. It'll come up at some point, but I probably won't focus too much, just to compare to this pressure gap, which has been around for a while. All right, so now it's time to quantize things, which is where it usually gets more murky. And so what I want to do here is I want to do harmonic analysis on a discrete set. So what's going to happen is my quantum Baker's maps will be n by n matrices. So this means they will be operators on L2 of Z mod n, where Z mod n is just the set with n points, numbers from 0 to n minus 1. And my n will be going to infinity. This will be my high energy or high frequency limit. Now, if you look at this group Z mod n, there is a well-known discrete Fourier transform in it, which is defined here. So this is a unitary operator. It's an n by n matrix with these entries, right? And that's something that will be featured. So this is the version of the Fourier transform I'll consider. Everything will be discrete, so it will be discrete Fourier transform. And then another operation, which is harder to define, not too bad, but it's I'll skip the formal definition of it, is a quantization of observables. So there is this thing coming back from quantum mechanics, that if you have a function of position and momentum, so let's say you have a function of two variables, x and psi, you can quantize it to an operator, really a family of operators, depending on the semi-classical parameter h, which in physics corresponds, I guess, to the Planck constant. And that's this classical quantum correspondence in quantum mechanics. You know how you when you quantize xj, you get multiplication by xj. When you quantize xij, you get minus ih partial xj. Then, Schrodinger operators, you have the classical Hamiltonians corresponding to quantum Hamiltonians and so on. So it's a fairly old idea, going back at least to the classics of quantum mechanics, I guess, to Schrodinger or von Neumann. So here we're going to do it, but my observable function, so this classical function, will be a function of a two-dimensional torus. My square, when I think about the square that I had before, I glue the sides to make it a torus. So if you have a function of a two-dimensional torus, turns out you can quantize it to a family of n by n matrices. where effectively this H Planck constant semi-classical parameter will be 1 over 2 pi n. And the advantage of this procedure is that you can use it to localize both in position and frequency at the same time in the asymptotic limit as n goes to infinity. So as I said, I won't define it, but here are some basic properties. If your function a on the torus is only a function of x, of the position variable, then this quantization is just a multiplication operator. I take my function a, which is a function on the circle, I sample it in the most kind of basic way. I just sample it at points j over n, right? There are n points like that. And I look at the multiplication operator by that. So it's just that it's a diagonal matrix in this case. Op n of a is a diagonal matrix with entries which are given by the sampling of the function a. Now, if a is only a function of the frequency, then you get the same thing, the same multiplication operator, but it's conjugated by the discrete Fourier transform. And these are the two cases that we will actually use today. So if your function is a function of psi only, then you're gonna get a Fourier multiplier, again, in the discrete setting. And here is a property that we don't use here, but it's good to know. So, if you have there's so many different things called quantization in different fields of mathematics and physics, and it's easy to get lost in all of them. But I think one thing that most people working on quantizations agree with is that commutator of operators, so commutator of these quantized observables, which are operators, here are matrices, corresponds to the Poisson bracket of the original observables. So the most general way to think about quantization, I think, is you have a symplectic manifold. Here is a two-dimensional torus, and then you want to map functions on this manifold to some operators on some Hilbert space, or maybe even something in a in a von Neumann algebra. But you want you always want a relation that looks something like this, that asymptotically, at least, as your parameter goes to infinity or 0, whichever your parameter is, the commutation of matrices corresponds to the Poisson bracket, and that's also true here. So by that standard, it is equantization. All right, so we have this way to convert functions on the torus to matrices. All right, so now this is this quantized observables, this op n of a, they're generalizations of multiplication operators, Fourier multipliers. In the manifold settings are generalizations of differential operators. Now, open quantum Baker's maps, they are of a different kind. You shouldn't think of them as multiplication operators. You should think of them as, well, in microlocal analysis, you call it Fourier integral operators. The difference between a multiplication operator and say one of those maps is that multiplication operator preserves the support of a function. It preserves where the function lives, and it preserves where the singularities are. These maps move it around. So you can think of these, if you're relating to more physically studied models, you should think of these maps as analogs of wave propagators. So the wave group or the Schrodinger group, which also moves singularities around. So here is actually the setting of, the specific matrices that we study are actually pretty easy to define. So here is the example how you do it for a mid-third Cantor set. So you take, I'm going to assume that my n is m to the power k. It's not actually needed, but it will make my life easier in other places. So I'm going to assume that the size of the matrix is the power of the size of the alphabet. Not the size of the alphabet, but the base. So for example, if you're looking at a mid-third Cantor set, I want my n to be 3 to the power, to some power. And then you look at an n by n matrix. So this 3 to the k by 3 to the k matrix, which looks as following. You take the adjoint, so the inverse of the Fourier transform, the discrete Fourier transform, that's a very explicit matrix. And then you multiply it by this block diagonal matrix, where the diagonal elements are, well, there are only two, corresponding to 0 here and 2 here. And they are the matrices of Fourier transforms of order n over 3. So, if you like matrix algebra, this is it, right? I wrote it as a matrix, except this open quantum Baker's map, it has discontinuities because if you're just to the left of the line of, say, of the mid-third line, then you're mapped somewhere. And if you're just to the right, then you're thrown out. And these discontinuities don't work well with microlocal methods. And in some sense, they are artificial anyway. So we cut off from them by multiplying by some cutoff function, which is smooth and compactly supported on the interval 0, 1. So this is this chi n over 3, chi n over 3. These are just diagonal matrices with diagonal entries, just sampling of some nice cutoff function. Yeah, so that's the matrix. You can see immediately that the norm of this matrix is no more than 1, because my cutoff is bounded by 1. So norms of these operators are no more than 1. This Fourier transform is unitary, and the other Fourier transform is also unitary. Right? And I should say that if you have a general Bayesian alphabet, it's defined exactly the same way. You can just stare at this formula and you can figure out how it should be defined. You just have this block diagonal, and the alphabet tells you at which points you're going to get these contributions, and the points not in the alphabet on the diagonal you get. So why is this a quantization with Baker's map? Well, this is the part of the talk where it gets, I guess, the most vague. So it turns out that you have this version of Yegorov's theorem, which is a version of classical quantum correspondence. Now, the usual Yegorov's theorem tells you the following. If you take a quantized observable, which is an operator, and you conjugate it by the wave group, then modulo low order terms, you get quantization of the result of propagating this observable function by the geodesic flow. Somehow the geodesic flow is intertwined with the wave group. Now here, the analog of our geodesic flow is this quantum map, which is is this classical Baker's map. So this kappa blah is this map that I drew on one of the previous slides, turning this flag into this flag. But this map isn't everywhere defined, and this Bn is not invertible, so you cannot conjugate, right? You cannot write Bn inverse. Instead, what you have is you have this version, which is an intertwining relation, right? If you could write Bn inverse, it really means one conjugates to the other modulo lower order terms. And then the relation between the symbols that you want here is that one is a pullback of the other one by the map, as long, but only in the domain of the map, and actually only in the support of this cutoff chi. So for example, if your A does, if your A does something in this middle third, then it really doesn't matter for this theorem. So for example, you could put B equals to 0 and A be supported in this middle third strip. And you just see that if you take this and you apply this matrix, you get 0. And why is that? That I actually can explain. Because you see you have this middle 0 here, right? It's as silly as that on the first step. So you know that if you have a function that's supported in the middle third of the interval 0, 1, and discretized by n points, then it's just going to be killed by that, right? And so that's why somehow if you have an operator that does something there, it is just killed. So it doesn't matter what it does there. And likewise, whatever you apply this matrix to, you're going to get something that's Fourier supported in the first and the second third of the interval. Okay, so that's why it's a quantization. You can actually show it's an explicit computation to show that this is a quantization of this map. So that's how it maps things around. It maps singularities around by this map, and it obeys this rule that you throw out the middle, and then the rest you stretch in position frequency like that. All right. So what I'm going to study are the eigenvalues of this matrix. So I'll call them resonances, and this matrix is norm bounded by 1, but it's certainly not unitary for one, because of cutoff, but also because of throwing out the 0 here. So you expect that eigenvalues will be inside the unit disk. And so I'll call them resonances. So this is similar to how if you consider the wave group on a compact manifold, then it's a unitary group. And so the eigenvalues of that would be on the unit circle. But here we have something that's subunitary. So eigenvalues would move inside, and that corresponds to somehow having real and imaginary parts of resonances. With the imaginary part of resonance, the speed of decay corresponds to the absolute value of the eigenvalue. So how far you are into the circle. All right. So now it's time to show some numerics, right? So a picture speaks 1,000 words. So I'm going to show you numerically what all the results here are, basically. So here is a numerical picture. the matrices are, are introduced in the previous slide. One great thing is that these matrices are really, really easy to write up and compute. Well, subject, of course, to the fact that if your n is very large, then your computer will struggle. I remember I was talking about this thing at some point to Alan Edelman at MIT, and he just pulls up he uses Julia, which he is the creator of, and he just pulls up Julia, and in I think about 45 seconds, he coded up the matrix and plotted its spectrum. So it's very, very easy to do. That doesn't require any kind of hard work. Just the usual computer algebra system, the usual systems can give you that quickly. And so it's very appealing to actually plot them and see what happens numerically. So here I took m equals to 5 just for the fun of it. So that's my base, and my alphabet is 1, 3. And here is k equals, k equals 1, I didn't draw. I guess it would be too silly. K equals 2. So this matrix it's a 5 to the power 2. So 25 by 25 matrix. How many eigenvalues do you see? So I see 1, 2, 3, 4, 5, maybe 6, right? You should have 25 eigenvalues. And you don't see that many, right? But the thing is, a lot of them are at 0 or near 0. At least 15 of them have to be at 0 just when you look at the matrix. All right, so let me dial it up a little bit. So you get, this is k equals 3. This is a 125 by 125 matrix. Here's the spectrum. And the circle is the unit circle. So we know the spectrum is in there because the norm is bounded by 1. Okay, this is a 625 by 625 matrix. And this is a matrix of size 3125, if I remember correctly, 5 to the power 5. Now you can see two features on this picture. I'll do the movie for you again. So start like that, and then grows, grows, grows. One thing that you see is that the spectrum does not appear to approach the unit circle. So it seems to stay strictly inside. And that's the spectral gap. I'll explain how this is proven. Another thing, which is not something that I'll probably have time to talk about today, but is also cool to study, is the number of eigenvalues in any fixed annulus. You cut away a neighborhood of 0, think how many eigenvalues there are. And you see when I shift here, this one really doesn't look like 3,125 eigenvalues, right? And that's because most of them are very close to 0. So if I count any fixed annulus away from 0 as the k goes to infinity, what I actually get is I get, instead of 5 to the k, I get 2 to the k here. So this is roughly this kind of big thing, thing outside of this cloud at 0 is roughly 32 eigenvalues. Not exactly, but you can count, you can kind of imagine that. So every time the size of the matrix gets multiplied by 5, but the number of eigenvalues in any fixed annulus roughly doubles. And so this corresponds to the number of eigenvalues growing like the size of the matrix to the power delta, which is a version of a fractal Weyl upper bound. Okay, so that's a numerical demonstration. And so now it's time to talk about some results. So the first result, and the only one that I think I'll talk about today, is a spectral gap. So how do we formulate a spectral gap? Let's define the spectral radius of this matrix, Bn. And then our claim is that this radius is strictly less than 1 in the limit as n goes to infinity. And the way I write it is I write the spectral gap as m to the power minus beta, where beta is a positive number. So this is another way to write a number that's less than 1. But this convention is useful because my initial map has expansion rate m. So if you want to compare it to results as a hyperbolic surfaces, that's the number that you should be thinking about as the size of this gap. So it's going to be convenient to write it like this. Then we can actually compute and estimate what the size is of this gap, at least that we can guarantee exists. Right. So yeah, so you have this, the spectrum never reaches the unit circle, and asymptotically it has this, lim sup is bounded by this number less than 1. And I should say that not only we show that this beta is bigger than 0, we also show it's bigger than half minus delta. Well, delta is the dimension, and this half minus delta is exactly the pressure gap. So this is this all gap that's been around for a while. And this pressure gap only makes makes sense to talk about it under the pressure condition, which means that the dimension of my Cantor set is less than a half. You see, in the setting, it's very easy to formulate what all of these fairly complicated quantum TS results mean. So if the dimension of Cantor set is less than a half, then there was already a gap known, basically, which is half minus the dimension, and we improve over that. And if the dimension is greater or equal than a half, then we show there is a positive gap, which would be a new result as well. All right, so so here is an example. Again, since we can do numerics, it's interesting to compare how the gaps compare. So here's my set. So here the dimension is log 2 over log 5, because I have two alphabet of 2 entries base 5. So log 2 over log 5 is less than a half, right? Because 2 square is less than 5, I believe. So so you get a pressure gap. It's in green here, and our gap is better than that. This is this blue, and you can see that here it appears to be right on the nose, in the sense that it really recovers the what the spectral radius is. Right, there is an eigenvalue right on this circle numerically. Well, if I take this alphabet 1, 3 and I switch it to a very similar looking alphabet 1, 2, then I can see that my eigenvalues move in a lot more, and so this theorem that we prove, it's an upper bound on the spectral radius, but certainly not a lower bound. Much more insight would be needed to understand what the exact spectral radius is. So things could, in some sense, we give a guarantee of some exponential decay, but there could be faster exponential decay, and that's actually hard to rule out. All right, so okay, here is some previous work. There was work on Nonon and Masher-Zworsky, which used different quantization, which kind of so-called Walsh quantizations, where they recovered that actually sometimes you have no gap, but the principal tool that we use, FractalUncertainty Principle, would not apply to Walsh quantization. So that actually explains the difference. And then there is a lot of work, I'll just flash it here, on more general hyperbolic systems, hyperbolic surfaces, hyperbolic manifolds, general open hyperbolic systems with XCMA flows, obstacle scattering, and so on. All right, so there's been a lot of studies on that in the general sense. All right, so now it's time for me, I think, to pivot to FractalUncertainty Principle, which is the main tool that's used in the proof of this gap. So this is where it's again going to get a bit vague, unfortunately. The actual proofs are not that long and difficult. Our paper is long because we did a lot of various kind of cases and special situations and stuff, but the actual core proofs are not long, because in this setting you don't need to know any heavy-handed microlocal analysis. Actually, everything can be done by hand. But I'm still not going to present them here. So what you do is, let's assume you have an eigenfunction, so an eigenvector, right, of your matrix Vn, with some eigenvalue lambda, and let's say it's separated away from 0. And I'll normalize my eigenfunction to be norm 1 and L2. So okay, so this is the part that's going to be probably most vague and confusing. Well, you'll just have to believe me that this Yegorov's theorem that I drew before, it was this Yegorov's theorem with holes, where sometimes if you don't care, you can iterate this Yegorov's theorem many times. And what I'll do is I'll iterate, so it corresponds to looking at propagation of your quantum system for k times, where k is this number. So n is m to the power k. So it's like logarithm of n, this k. Technically, you should propagate a little bit less than that, but I'm not, the stuff in gray, I think you can safely ignore it for the purposes of today's talk, but to be mathematically correct, I should keep it there. And then this Yegorov's theorem, what you do is you get this kind of relation with some low order terms and blah. And you need these two symbols to be related to each other by pulling back by this by the power of this open Baker's map. But it only has to be so on the domain of this map. So what happens outside of the domain does not matter. So somehow, because it's things in the phase space that we threw out at one of the steps of the iteration. And so recall that, right, so here I have this bk to the n. And so my u is an eigen function. So bk to the nu is just lambda to the ku. Right? That's where I use it's an eigen function. So that's the change I made here. And then remember that the domain and the range of my map are given by this set gamma plus minus k, which correspond to either making x or making psi. So either position or frequency should be in this discretized Cantor set. So that's going to be important. So I'm afraid this picture is going away now. So if you look at this theorem, you can get two corollaries. One corollary is I can take A equals to 1. So this means this would be the identity operator up and of A. And then B, you just need it to be 1 on the range of this map, because that's, then this relation is still satisfied. And then you see that your eigenfunction U is going to be equal to this quantization of 1 gamma k plus, so this is the indicator function of gamma k plus u plus O large of n to the minus infinity. What this means in practice is that eigenfunctions, modulo, they are essential support. So if you forget about this kind of very small error terms, this is decaying faster than any negative power of n, they will be essentially supported in the Fourier space on the Cantor set. You can actually see it. I'm sorry I didn't put more numerics here, but if you numerically compute an eigenfunction of this matrix with eigenvalue in some annulus, so don't go too close to 0, and then you plot the discrete Fourier transform of that, you will see that it will have big peaks near the Cantor set, and everywhere else it's going to be extremely small. So you have some eigenfunction that really lives on this Cantor set in the frequency space. Now you can do a similar thing where you put B is equal to 1, and then A can be the indicator function of the domain of this. What this gives you, and this is less intuitive to see, but what this gives you is that if you look at the mass of your eigenfunction on the Cantor set in the position space, then it's bounded below by lambda to the k, where lambda is my eigenvalue, and the absolute value lambda to the k. So you get something that's, that you have an eigenfunction, which is localized in the Fourier space in this fractal set. And you know that you have a lower bound on mass of this eigenfunction in the position space, also on the same fractal set, because this gamma k plus, this operator here, corresponds to localizing, the red operator is localizing in frequency to the Cantor set, the blue operator is localizing in position to the Cantor set. And so you can get a contradiction if you can show that the product of the blue and red operator is decaying. And your lambda is sufficiently close to the unit circle. So that's how you get the spectral gap. So what we will show is this fact called fractal uncertainty principle. I'll reformulate it in more palatable way on the next slide. But what it tells us is that no function can be localized by both the red and the blue operators. So if I take the product of these two operators, each of these has norm 1, but their product has operator norm decaying like n to the minus beta for some positive beta. And that's the size of the spectral gap. And then you see when you compare these two statements, you see that u is this red operator times u, then you just apply the blue operator to that. And you get you get a lower bound, you compare it with the norm of this operator, and you see that your lambda cannot be bigger than m to the minus beta in power. Right, somehow, so imagine if your lambda had size 1, for simplicity, imagine you had an eigenvalue exactly on the unit circle, then u is equal to up n of, u is equal to the red operator times u, and then the blue operator times u would still have norm 1, but that cannot be because the blue operator times the red operator times u has to be small. And so how small this beta gives you how far inside the circle the eigenvalue should be. So that's where that's where the spectral gap comes out. So what's left is to prove this fractal uncertainty principle. Now, we described what these blue and red sets are. They are drawn here again. And so you can rewrite it. These operators, one of them, the blue operator is just a multiplication operator, discrete one. And the red one is a multiplication operator conjugated by Fourier transform, which is unitary. So when the dust settles, you can rewrite this fractal uncertainty principle and in the following simple form. So the good news is that if you zoned out during the previous part of the talk, you can restart from here if you don't care about the application and just look at it as a problem in itself. So you have a large number n that's a power of m, let's say a power of 3, let's say mid-third Cantor set. So n is 3 to the power k, let's say here. Fn is the matrix of the discrete Fourier transform, is unitary. This 1ck is just a multiplication operator by the indicator function of the discrete Cantor set. So if you look at this matrix, so this is just diagonal matrices with zeros and ones on the diagonal. If you look at this product, you can think of it in terms of matrix algebra as follows. You take the matrix of the Fourier transform, and you only leave the rows and the columns that are in this mid-third Cantor set. And you want the operator norm on that. You want the operator norm bound on that, which is decaying as some negative power of n. That's what the fractal uncertainty principle is for us in this setting. So, yeah, and again, the way to interpret it, why is it called an uncertainty principle, is because it tells you that no function can be localized on this Cantor set in both position and frequency. Right, because if you had a function that's localized there in both position and frequency, then when you multiply by 1ck, you get the same function back. You take the Fourier transform, then you get something that's still localized on ck, and so you just applying it to this function, you get the same norm, which would contradict this norm bound with beta bigger than 0. So what kind of bounds can we get for this matrix? Well, you can of course always show the norm is bounded by 1 just because it's a product of 3 operators with norm 1. You can also use the Hilbert-Schmidt norm. That's a neat calculation. You can, the operator norm of a matrix is bounded by its Hilbert-Schmidt norm, which is just square root of the sums of squares of entries, which are very easy to compute here explicitly. And then you see that you get a bound with beta equals half minus delta, which is exactly the pressure gap. So that's what the pressure gap looks like. And so in order to prove our theorem, so to get a better gap, you need to show that you actually have a bound here, which is better than this pressure gap and better than 0. So you do have decay. All right, that's what it says here. Right, and that's something that would require the structure of the fractal set. Somehow, in all of these considerations, I used at most the number of elements in the fractal set. To improve over that, you actually need to use its fractal structure. And that's done on the next slide, I believe. Yeah. So here's a theorem. So this is a fractal uncertainty principle for this Cantor set with some exponent that's bigger than kind of the basic ones. So how do you show this? Well, the majority of the proof, but it's kind of it's a part where Cantor sets are really useful, but it's also a somewhat boring part, which is why I skip it here, is that it turns out that if I look at these norms of these matrices, I have submultiplicativity. So what are the matrices? So I take any k. Again, imagine I do the mid-third Cantor set. So my n is 3 to the k. This is a 3 to the k by 3 to the k matrix, where I just take the Fourier transform and I replace by 0 all rows and columns with which are not in the Cantor set. The indices are not in the Cantor set. So I look at this norm, and that depends on k, right? For any k, I can form this. It turns out that the sequence is submultiplicative. That kind of exact submultiplicativity with any constants or anything here, or any error terms, is very specific to the Cantor sets. And the reason it's there is, the way I usually explain it is you can write this matrix for k plus L in terms of a tensor product of the matrices for k and L and certain twist factors. Just like, if you know how fast Fourier transform algorithm works, It works by decomposing a big Fourier transform in terms of Fourier transform, say size n/2, and it's a similar procedure here. So you can really write out this matrix and decompose it and get this submultiplicativity, in a way inspired by fast Fourier transform algorithm. Once you have something that's submultiplicative, it means that in order to get this asymptotic bound, all you need to show is that one of these norms is, let's say, less than 1, if you want this to exponentially decay. If you have a submultiplicative sequence and one of the elements is less than 1, then the sequence is exponentially decaying. This is not too hard to prove. I forgot Fikit's lemma. I forgot now, but there is a standard word for it. So how do you show that this matrix has norm less than 1 somewhere? Well, if it has norm equal to 1, this matrix has norm no more than 1. If it has norm equal to 1, then you can find something that achieves that norm, and that gives you a function which is localized exactly to your set, Cantor set, in position and in frequency. Well, localization and frequency to the Cantor set means that its discrete Fourier transform is 0 on the complement of the Cantor set. Now, discrete Fourier transform corresponds to evaluating polynomials at roots of unity. So I form this polynomial with coefficients of this matrix of my counterexample function, and I see that this polynomial has to have a lot of roots, because any root of unity with index mod n, with index that's not in the Cantor set, will give me a root, and then with a little bit of work, you can assume that the last element n-1 is not in your Cantor set, and that gives you that the coefficients of this polynomial are only non-zero when j is in the Cantor set, and so you can use that to have an upper bound on the degree of the polynomial. On the other hand, you have a lower bound in the number of roots. If you compare these two quantities, you see that when k is large enough, the number of roots is larger than the degree, and so that cannot happen. And that's how you get your contradiction. Okay, I think that's, don't worry. The rest of the slides, I think, were about the fractal Weyl law. Well, there is something about how to improve over the Hilbert-Schmidt bound. And then I think it's a good place where I can stop the talk, actually.
Well, thank you very much, Semyon. Are you really finished?
Yes, I can. Yeah.
Well, you gave a very beautiful overview of the fractal uncertainty principle, and I think it's now going to generate a great deal of discussion. So perhaps I stop sharing your screen for a moment so we can see the audience, and I hope that people who ask questions will turn on their video so we can see their face. Are there any questions?
Yes, I have a question. Paolo Jorgensen here.
Yes, Paolo.
I just want to call attention to big literature, especially in the last decade or a little more. I guess the key word there is iterated function systems, and that includes both the kind of Cantor systems you showed and some of the conformal ones. I guess the thing that was not stressed so much in the beginning of the talk was what's called maximal entropy measures. So that each of these Cantor type limit constructions have a unique fractal measure that allows us to do a fascinating Fourier analysis on L2 of these fractals. And one of the things that I've been involved in is identifying the particular fractals that admit an orthogonal Fourier expansions and those that do not. And so both of them interest, but and so there's also associated uncertainty principles for that. So I guess my question is if you've made connections to some of the work on harmonic analysis on fractals.
So surprisingly, it's we were not able to somehow do it because mean, I am, of course, you know, I know there is a lot of excellent research on things, for example, you know, defining diffusion processes, Laplacians on fractals, right? Harmonic analysis on fractals themselves.
Yeah.
But
the communities that do different kinds of, the one that I've been involved in is, I guess I did a CBMS lecture 2 years ago. We called harmonic analysis, smooth and non-smooth, and the non-smooth part was the fractal part. But there are many communities, and Bob Strickard is
right.
But Bob Strickard stresses Laplace operator analysis, and I stress orthogonal expansion analysis. But anyway, I guess maximal entropy is a key part of the analysis. Yeah,
it's somehow what we do is more like the harmonic analysis is the usual one.
Yeah, right. Yeah,
but you restrict everything.
Right. Yeah. So you get
to the fractal set.
You get a
yes.
Yeah.
I mean, it's conceivable that some of it should be related, but maybe nobody looked into that very carefully, because you know the question as I formulated it in this discrete setting, you can't think of it as fractal analysis on harmonic analysis on this Cantor set, but it's a bit different, because you know I take the matrix of the discrete Fourier transform, and I restrict that one to the fractal set. And when you restrict it to the fractal set from a point of view of harmonic analysis, it's not so nice. It's no longer unitary, right?
Oh, right. Yeah, sure. So there's some special cases where you get unitary.
Right. That's actually. Let me show you one slide.
Okay.
I'm going to use this as an excuse to show one slide. So there is blah blah. So there are, in this particular model, so this is very, very special in our setting to this particular model, you can choose some very particular alphabets, which is where this restricted matrix of the Fourier transform becomes a constant times an orthogonal a unitary matrix.
Yeah.
So this is called, well, I call them special alphabets, but there's really corresponds to the alphabet being a spectral set. If you do a little bit more, which means that the Fourier characters, when restricted to the fractal set, they have you can find an orthogonal basis of these.
Yes.
And so for these special alphabets, you also see interesting things for the associated open quantum maps. It's not completely clean, but you can see that there is this magic circle of where beta is 1/2 minus delta over 2, where you see eigenvalues on the circle and then everything inside. And no matter which system you take, it numerically looks this way. This one is particularly nice.
That's related to your transfer operator, right?
Yes. And so we
on Frobenius analysis.
Oh well, this is the open quantum map. So this matrix with the Fourier transform, which is it's kind of a transfer operator, but in the discrete setting, you cannot define a transfer operator, because if you have a function defined on numbers 0, 1, 2, and 3, you cannot define this function at 1/3 a priori, right? So there is some Fourier transform on cutoffs but yeah, it is kind of a transfer operator. And so we have a conjecture that you should have a kind of this picture should hold, namely you have this ring of resonances and their number should be exactly onto the delta, which would be exciting because this would give a first fractal lower Weyl bound, which is something that's a big open question. And then you have a gap after it. But that's something that we were not able to prove. We worked on that, but the classical quantum correspondence is a subtle thing, especially when you get very close to the set.
Right.
But yeah, so these things, and I should say these spectral alphabets, of course, it's conjectured by Fouglid. that they appear only if the set tiles Z mod M by translation. So that's still an open question.
The full question was a big inspiration for my work too.
Yes, I mean, it's false in higher dimensions. I think
Right.
dimension 3, it was disproved by Terry Tao, but in dimension 1, it's probably true, but nobody knows how to prove it.
Yeah,
Anyway, so
it's open in dimension 1 and 2, yes.
I'll stop sharing again. But a very good question.
So are there any other questions? So maybe I ask, in some approach to uncertainty principles, one has a Hausdorff-Young inequality for the Fourier transform. Is there anything like that? Because that leads to entropic uncertainty principles.
So I'll reinterpret this question as, can one do something using LP norms?
Yes.
I know this is but that's I'll make it a more broad question. Can one do something using LP norms? So okay, let me share the slides again. There are a couple of things here about that. So one is this Hilbert-Schmidt norm, or where is it? Is it you see, you can think of this Hilbert-Schmidt norm also, the bound, or this volume bound, in this way, that you use the fact that the norm of the Fourier transform from little L1 to little L infinity is bounded by m to the minus a half, which is the endpoint case kind of Hausdorff-Young, right?
Yes.
So that's something that one uses.
Yes.
But then you think.
So then if you have an L2 norm, you have an interpolation.
Right. So you think, can you do something using LP norms? I mean, the kind of, here's a picture you get. This is the horizontal is delta, the dimension of the fractal set, and beta is the numerically computed fractal uncertainty exponent. You can see the picture is pretty complicated. The ones on the dashed line are the special alphabets that I talked about in response to the previous question. They're in some sense the best. But what happens here is that basic LP bounds, if you only use volumes of sets, which is if you use LP bounds just like that, you're only using volumes of sets. If you rearrange your set to be, an integral of the same size, it shouldn't change. Will only give you this half minus delta, which is this line.
Yeah,
now
so you put in some local structure in the set.
Right. So what you can do, and that's actually the first time I think fractal uncertainty principle was proved, was using additive combinatorics, which is if your dimension is close to 1/2, what you can do is you can use Holder's inequality with L4. So you use the volume of one of the sets. And then if you look at the L4 norm of the Fourier transform indicator function of the set, that corresponds to something called additive energy, the number of solutions to equation A plus B equals C plus D. And that's where you can see that Cantor sets are special, because if you're solving the equation A plus B equals C plus D, and A, B, C, and D are in the, say, mid-third Cantor set, it's pretty rare to have solutions to that. So most A, B, C would not have the property of A plus B minus C is also in the Cantor set. And so you can get an additive energy gain for these Cantor-like sets using their structure and combine it with Holder to get an improvement near 1/2. And that's, that's been kind of superseded by other results later, but actually that's where the best gain comes out from. So there are other situations, if you knew that I think in terms of classical harmonic analysis and LP bounds, the best thing would be if somebody proved that fractal sets have a very good Fourier restriction bound. Or, just a very good Fourier decay bound, or, some kind of LP to LQ bound for Fourier transform just on fractal sets. And that would give you, a stronger fractal uncertainty principle, but that does appear to be a very difficult question in general. But that's where, a lot of the kind of classical harmonic analysis improvements in LP to LQ estimates are due to curvature, right? Like things like Thomas Stein, for example, use the curvature or decoupling for that matter, which is a more recent advance. You use curvature, you're thinking, here we don't have curvature, we have fractal structure. But again, we want to say that our sets somehow are lacking additive structure, so you should have some Fourier improvement. But it's hard to to quantify. I know later on, I worked on these things with Bourgain, who was, a force of nature in harmonic analysis, and I don't think he proves fractal uncertainty principle in general in dimension 1, but even he somehow could not relate it to these decoupling and other things that he was, of course, a great expert on.
Well, it looks like there are many open questions and much work to be done in the future. Yes,
maybe not always for me, because I'm not a harmonic analyst by training, or maybe even in spirit, but I'm always looking for somebody who knows how to prove these bounds, because I have good applications for some of them.
So are there any other comments or questions? Well, if not, I'd like to thank Semyon again for a beautiful talk, and we look forward to seeing you again next week. Bye-bye.
Thank you. Have a good one. Thanks a lot for inviting me, and have a good rest of your morning.
Thank you.
Bye
Thank
now.
you. Bye.